We will now have problems involving polar coordinates. So the first problem here says that we're going to convert the Cartesian point 3, -3 to polar coordinates. So basically what we're going to do here is to change our x to radius and our y to degree. That is the meaning of changing from Cartesian point to polar coordinates. So our x here is 3 and our y is -3. You know that. So the r here actually is radius. So we're going to change our x to r. And our y we're going to change to degree. As I said, this is basically degree with respect to the positive x-axis. Okay, so how to do this? Of course, to get the radius, we are going to use the distance formula, which is the square root of x squared plus y squared. So that would be the square root of 3 squared plus -3 squared. So this is square root of 18 or equal to 3 times square root of 2. Okay, because that is 9 times 2. Square root of 9 is 3, so we put it outside. Now, to get the degree, the formula is tan theta. Tan theta, we have y over x. So this is -3 over 3. The answer is equal to -1. Then theta is equal to shift tangent of -1. The value is actually -45 degrees or -pi/4. Okay, so this is how to change our Cartesian point to polar coordinates. Our x becomes our r and our y becomes our degree. Okay, so if you're going to graph this, actually, this is our x and this is our y. 3 -3 is here. This is 3. -3 is here. So 3 -3 is on the 4th quadrant. This is the first, the second, third, and fourth. Now looking at our degree here, -45 degrees or -pi/4 is also in the 4th quadrant. So we don't need to adjust this. Our final answer is 3 times square root of 2, comma, -pi/4. Okay? Because it is already on the 4th quadrant. All right, so this is basically how to change to polar coordinates. It's very simple. We use the distance formula to get the r or the radius. Okay, and we use tan theta to get our degree with respect to the x-axis positive, this line. Okay, from 0 to positive infinity. Right, so let's proceed to number 2. Here you are asked to find the Cartesian coordinates of the point given in polar form. So this is basically the opposite. Here we are given the polar form. R is 4, that is our radius, and our theta, the angle, is pi/6, which is actually 30 degrees. because pi is 180 and divided by 6 is equal to 30 degrees. Okay, so this is the opposite. Our form here is r theta 4, and we have pi over 6. So the formulas actually for x equals r cosine theta, and y is r sine theta. Okay. So using this formula, we can just plug in our value or the values given here, and we can get our x and our y. So please remember these formulas to change the polar form into Cartesian coordinates. So our x is equal to 4 because our r is equal to 4. It's this one. And our theta is pi over 6 or 30 degrees. So 4 cosine pi over 6, okay, that is equal to 2 times square root of 3. You may check this in the calculator. And y is equal to 4 sine, we have pi over 6, and that is, of course, equal to 2. So our answer here is 2 times the square root of 3, comma 2. Now you can check this one, of course. Yeah, you can check your answer using the distance formula. Now our r is equal to 4. It is our distance from the origin. This is our x and this is our y. So the formula to get the distance actually, r here, is equal to x squared plus y squared. So r is equal to, we have 2 square root of 3 squared plus 2 squared. So r is equal to, this will become 4 times 3 plus 4, which is equal to 4 exactly. Because we have 12 plus 4 is equal to 16. Square root of 16 is equal to 4, which is equal here. So this means that our values here, the x and the y, are correct actually. Okay, so this is how to convert from the polar form to the Cartesian coordinates. It's the opposite of number 1. Here, we have the Cartesian form or Cartesian point. We change to polar coordinates. So it's the opposite, right? So I hope this is clear. Now, number 3, you're asked to actually sketch the polar curve. R is equal to 2 plus 2 cosine theta. Okay, first let's check if we have a symmetry here by assigning some values to our theta, positive and negative. So to test the symmetry, actually, we have to assign negative theta and see if the answers are the same. So assuming that we're going to use, for example, positive 90 degrees, using the calculator, the answer is 2. And how about our negative 90 degrees? Using the calculator, the answer is also 2. So this one is actually symmetric with respect to the x-axis. Okay, so it means that above the x-axis, it will be symmetric below. Okay, if we're going to graph. Now, starting with theta equals 0, we're going to find our r. So using the calculator, you're going to have 2 plus 2 cosine 0. Here are cosine theta. We can change this directly to 0. The answer here is actually 4. Okay, so it's here. This is our plane. Actually, when we talk about polar coordinates, this is our system. Okay, so it's entirely different compared to the Cartesian plane. All right, so for 0 degree, the answer is 4. Let's try 30 degrees. That's 2 plus 2 cosine 30 degrees in your calculator. The answer is 3.7. And for 60 degrees, okay, we have actually 3. And 90 degrees, we solved this already above. It is 2. And 120 degrees, answer is 1. 150 degrees, 0.3, and 180 degrees equals 0. Okay, so we usually stop until 180 degrees when we are graphing, a polar curve such as this one. All right, so 30 degrees is 3.7. This is 30 degrees. So this is 1, 2, 3, 3.5, 3.7 somehow is here. Okay. And the next one is 60, which is 3. So 1, 2, 3. And 90 is 2. 1, 2. 120 is 1. This is our 120. 1 is here. And our 150 is 0.3. So approximately here. And 180 is 0. Okay. So if you're going to connect that, it's going to be like this. Okay. So since it is symmetric, it will be actually like a mirror here below. Okay. So that means the next here will be opposite of 30 degrees. Okay. So this is 345 actually here. That's 15. So it will be here. Okay. And then the next one is, so we have 30 here. Next will be 300. Okay. That is, of course, 3.7. So here we have, as you can see, we are having 15 and 30. So we are going to follow this one. Okay. So the distance here is 15. Then we have 30. So the next one is 300 for our partner here. So we have 4 already. Okay. 4. And then here we have 3.7. Okay. Right. Next is, okay, so we are not going to include this one because it is 15. So we need this line because our interval here actually is 30. So next to that is 3. So this is 1, 2, 3. And then here we have 2, then we have 1, and then 0.3, then it comes back to 0 again. So if we're going to connect all of this, okay, so this is our graph actually using this polar curve, okay? So since it is symmetric, we have to follow exactly the values here using the same interval counterclockwise. The first set we have here is actually counterclockwise, and the other one here down is like clockwise. Okay. Well, it's up to you how you're going to do it. Usually, when we start from 0, 0 is here, then we have 4, then we go to the next. This is counterclockwise. Okay. And for the one down, you can have the same actually going to the left. Okay. It's also counterclockwise, but it is basically negative. Okay, so that's why it keeps on going down here. 360 it becomes 345 because minus 15 is negative actually. Okay, so since it is symmetric, the one above is a mirror image of the one below. Let's proceed to number 4. You're going to determine the area enclosed by the curve r is equal to 3 sine theta. So what are we going to do here? The formula of an area actually enclosed by any polar curve is 1/2 of the integral from the lower limit to the upper limit r squared d theta. So our r is given, that is 3 sine theta. So we can immediately solve our a, that is 1/2 from 0 to pi. Usually pi is 180 degrees, like what I did here. We stop at 180. Usually when we talk about a polar curve, we use values from 0 degree to 180 degrees, usually. Okay, so let's plug in our r, that is 3 sine theta squared d theta. So this becomes a equals 1/2 from 0 to pi. This becomes 9 sine squared theta d theta. Okay, so the next thing we're going to do is to, of course, put our 9 outside. Okay. Then sine squared theta actually, that is 1 minus cosine 2 theta over 2. Okay. D theta. And now we have here a 9 over 4 outside. Why? Because we have 9 over 2 here times 1/2, it becomes 9 over 4. Usually, we have to put the numerical coefficient on the left before the integral sign. So this is from 0 to pi, 1 minus cosine 2 theta d theta. Okay? So why this is 1 minus cosine 2 theta over 2? This is basically the equivalent of this, sine squared theta. So we can easily perform the integral or evaluate our integral. Okay, so let's proceed to the last here. Our answer is 9 over 4. Okay, we have one here, so that would be our theta, minus cosine 2 theta is actually sine 2 theta over 2. Okay, that is the integral of this. And this is from 0 to pi. Okay, so 1 minus cosine 2 theta, we are actually integrating this by parts. The first one is 1. Okay, you know that if we have a constant, it's going to take the variable. For example, if it is 5, okay, like 2x plus 5, if you're going to integrate this 5 becomes 5x, and 2x becomes 2x squared over 2 actually. Okay, so here we are not using x. Instead of x, we're using theta actually, because we have 3 sine theta. So instead of using x, we use theta here. Okay, or 1 theta or 1x actually, if this is x here. And cosine 2 theta actually is sine 2 theta over 2 because of the 2 here. So we have to divide by 2. Right? So please remember that. Now to identify our area, we have 9 over 4 that is outside. We're going to start with pi. Okay, so the first one is we have pi minus sine 2 pi over 2. Then the next will be 0. Okay, so minus, this is 9 over 4 actually, times 0 minus sine 2 times 0 over 2. Now this one is 0. Yes, because sine 2 times 0 actually is 0. And this one is also 0 here. So the answer is 9 over 4 pi. Okay, so that is the area of this polar curve. So we can put here units squared because it is an area. It could be centimeters, meters, kilometers. We don't know. It's not given. Okay, so we just use the word units. Okay, so let's try to review this once more. We are actually finding the area enclosed by the polar curve. Our curve, when you say curve, actually, it is a graph, because we can graph this on our polar plane. R is equal to 3 sine theta. Now, the formula to find the area of a polar curve is 1/2 times the integral from the first angle to the upper, so the lower limit to the upper limit of r squared d theta, because our variable here is theta. Okay, so we change our r into the given 3 sine theta squared. That becomes 9 sine squared theta d theta. So 1/2 of the integral from 0 to pi. 9 is outside because it is a numerical coefficient. Okay, and the value of sine squared theta is 1 minus cosine 2 theta over 2 d theta. Okay, so the next is to integrate. So we have 9 over 4 here outside because this is 9 over 2 times 1/2. Okay, and we put it outside. And the remaining is only 1 minus cosine 2 theta. Now to integrate this 1 minus cosine 2 theta, we integrate by parts, starting with 1. So for 1, the answer is theta. Okay, that is the integral of 1, because we're using theta as our variable. 9 over 4 is outside, and cosine 2 theta, that is sine 2 theta over 2. Whatever is the number here, it becomes our denominator when we integrate. Okay, so that is from 0 degree to pi or 180. So now we are going to replace starting with pi. Okay. So we have pi, change theta to pi, minus sine 2 pi over 2. This becomes 0. So the remaining here is 9/4 pi. And this will be all 0 because sine 0 actually is 0 in your calculator. So the answer is 9 pi over 4 units. Please take note that pi is equal to 3.14159. So you can change this into the value, divide by 4. So times 9, divide by 4, you're going to get the exact value. Okay. All right. So this is how to find the area. The next one is to express this actually equation in polar form. Well, this is already in polar form. This is the polar form. Okay, r squared. So we could see already our r there. This is the standard form. So the formula, as I mentioned, is this: x is equal to r cosine theta and y is equal to r sine theta. So you can replace it. This is r cosine theta squared plus r sine theta squared equals r squared. Okay, so this is r squared cosine squared theta plus r squared sine squared theta equals 9. That is our r squared here. So we have r squared outside, cosine squared theta plus sine squared theta equals 9. So this is 1 actually. Yeah, cosine squared theta plus sine squared theta is equal to 1. So r squared is equal to 9. R equals square root of 9. So r is equal to 3. Okay, so our radius here actually is equal to 3 using these formulas. Right, so that's it. This is how to express this equation into polar form and finding r. Now here we are asked to find the points of intersection of the polar curves. The first curve actually is r equals 2, and the second one is 2 cosine theta. Okay, you know that if it is point of intersection, what we're going to do is to equate our equations. Okay, like what we do in our, pure mathematics actually, in algebra. So this is r and this is r. 2 is equal to 2 cosine theta. We divide both by 2. So 1 is equal to cosine theta. So this one can be solved easily, actually. We have theta is equal to shift cosine 1. So here, the answer actually is 0. Right, so we can now plug in this value here. R is equal to cosine theta. So R equals cosine. We have here 2 cosine theta. So 2 cosine 0. R is equal to 2. So the point of intersection is r comma theta. So it is 2 comma 0. So this is the point where they're going to meet. Okay, so I hope this is very clear. These are some of the most important problems in polar coordinates. Thank you so much for watching. Until the next time, bye-bye.